Okay, this is exam 4 for physics 202. Current travels through a wire as shown. What is the direction of the force? So let your fingers go in the direction of I. Uh, your index, or excuse me, your index finger is the direction of I, your middle finger in the direction of B. So that gives a force to the left, like that. Magnetic fields inside the solenoid are as shown. What is going to be the direction of the magnetic field? Um, so the currents as shown. So let's just consider the current on this side. If we think about our thumb going in the direction, this direction, that's going to cause a magnetic field that is up. So C is the right answer. Consider this loop of wire. What happens as time continues? Well, it's going to turn clockwise for a half turn and then counterclockwise for a half turn. We can consider just say this side where the current is into the page and the magnetic field E is in this direction. So current into the page, magnetic field, that gives us a downward force. So to have a force that's down on this side and a force that's up on this side, initially causing it to turn clockwise, but when it goes around a half a turn, it's going to turn back the other direction. Consider this function. In which quadrant would you draw the phasor? And just if you forgot your quadrants, they're right here. So here I have a value that is negative and approaching more negative, so it'll be in the third quadrant. Remember, this is the y projection. This value is this value, and as this phasor moves more in this direction, it will increase. So at this point, my phasor will be in that direction. So C is the right answer there. Current carrying wires moving towards a conducting loop in the direction shown. As the wire is moving, is there a clockwise or a counterclockwise current or no current at all? So first of all, what is the magnetic field produced by this wire? Well, it's into the page there and out of the page where I have this loop. That magnetic field is increasing. That means that the induced magnetic field will be opposite the direction of the magnetic field. So I will have a magnetic field due to this that will be into the page. And in order to create a magnetic field into the page, I'm going to have a current that is in this direction, and that is clockwise. Faraday's law says that the induced EMF is caused by a changing magnetic flux. Okay, this is straight from the concept test. The answer here is B. These two will have equal forces, and then these two will also have equal forces. This is on the concept test. Here, an inductor is a coil of wire. An inductor is simply a coil of wire, nothing fancy about it. It's not a resistor, it's not solid state, it's not a capacitor. Point A is equidistant between these two long parallel wires. What is the direction of the magnetic field at point A due to the two wires? Well, due to this wire, I have a magnetic field that's into the page, out of the page. Due to this wire, I have a magnetic field that is into the page, out of the page. So over here, I have a magnetic field that is out of the page. What type of transformer we have outside our house? That is a step-down transformer. It takes it from high voltage to low voltage. Consider this circuit. A portion of the circuit sits in a constant magnetic field that's given by this, the 3I Tesla. What is the magnitude and direction of the force on this segment of wire? So here we just have to first find out what is L, the vector L. L is going to be x component of L in the I direction plus the y component of L in the j direction. That's going to be, well, this length of wire we're told is 0.5 meters. So it's going to be 0.5 cosine 60 I plus 0.5 sine 60 j. So my L then is 0.25 I plus 0.43 j. And then I also need to know what is my current. Well, my current is V over R. So that's 12 over 6 or 2 amps. Now I'm ready to do my force, IL cross B. So my force is 2 amps times L, which is 0.25I plus 0.43J crossed with my magnetic field, which is 3I. All right, these two, the cross product will be 0, so I'm not going to include that. So I have 2 times 0.43 times 3 times J cross I. J cross I, if I draw my coordinate systems, this is I, this is J, this is K. If I do my right-hand rule, I get that J cross I is equal to negative K. So this works out to be negative 2.6 K because J cross I is negative K. Right, here I have a mass spectrometer. I want to know what is the particle. Well, I know that R is equal to mv over qb. That's the cyclotron equation. So the mass to charge ratio is RB over V. That's going to be 0.5 meters, 2 Tesla, 2 meters per second. That's 0.5. So the mass to charge ratio is 0.5, and I go through and I look for which of these does the mass over this, that's 1 divided by 2, equal 0.5, so it is this particle, delirium. Consider this transformer. The primary coil has 4 turns, secondary has 8 turns, the primary voltage is 100 volts, and I want to know, this is NP, NS, I want to know what is ES. What is the secondary voltage? Well, I know that ES over NS equals EP over NP. So ES, the secondary voltage, is equal to that's 8 over 4 times 100. So it's 200 volts. Had some other questions. Is this step up or step down? Well, I'm going from 100 to 200, so that is a step up transformer. And then see what frequency does the secondary voltage oscillate. It oscillates at the same voltage as the primary voltage at 60 hertz. All right, consider this circuit. It's a LR circuit. Has an inductor, has a resistor, and has several questions about it. So first of all, what is the equilibrium current? Well, that's just from Ohm's law. So V is equal to IR. So I is equal to 12 divided by 3, which is 4 amps. In equilibrium, the inductor is like it's not even there. It just becomes a piece of wire. How long does it take to reach this current? Well, this is a exponential growth equation, and so the time required to reach this maximum current is equal to 10 times the time constant, which is 10 tau L is equal to L divided by R, which is 10 times 8 over 3, which is 27 seconds. How long does it take to reach 1/2 of this equilibrium current? So how long does it take to reach 2 amps? So it said this is a exponential growth. So I have E over R, that's my maximum current, times 1 minus E to the minus T over tau. I'm trying to solve for T here. See, I'll just go ahead and put in my numbers. 2 amps, 4 amps, 1 minus E to the minus T over 2.7, 2 over 4, minus 1 equals negative E to the minus T over 2.7. This is negative 0.5. Make those positive, do the natural log of both sides. And I get solving now for T, this cancels, and my T is equal to 1.9 seconds. In part D, I want to know what is the energy stored when it's at this current, that is, when it has a current equal to 2 amps. What is the energy stored? Well, UB is just 1/2 Li squared. 4 times 4 is 16 joules. And then finally draw a graph of this, of I versus T. It looks like this. It approaches this 4 amps. 4 amps, yeah, that's your equilibrium. Okay, single loop has a 10 ohm resistor, 5 Henry's inductor, and a 3 microfarad capacitor. Initially, capacitor is 6 microcoulombs and the current is 0. This is an LRC circuit, damped oscillator. You didn't have to draw it, but you could. So I have 10 ohms, 5 Henrys, and 3 microfarads. And then also the charge on that capacitor is 6 microcoulombs. So first thing I want to do is find the charge at a particular time. So Q is equal to Q times e to the minus RT over 2L times the cosine of omega prime t. You might be able to convince yourself that omega prime is equal to omega, but let me just show you. So omega is equal to the square root of 1 over LC, which is 1 over 5 times 3 times 10 to the minus 6. Just 258. That's in radians per second. That's our angular frequency. Now omega prime is equal to the square root of omega squared minus r over 2L squared. So since r and L are about the same value, well, this works out to be the square root of 258 squared minus 210 over 2 times 5, which is 1 squared, and that's equal to 258. So you see here that, as we had in our derivation, that omega is equal to omega prime. So we'll just take omega to be equal to 258. Now Q is going to equal to 6 microcoulombs. That's the maximum charge on my capacitor, what it has in the very beginning, times e to the minus 10 times 0.1 times over 2 times 5 times the cosine of 258 times 0.1. Be very certain that you have your calculator in radian mode on this, and you get 4.3 microcoulombs. Okay, so that's the answer there. And then for part B, I want to know, when is the first time the capacitor is 0? Well, you're just looking at our cosine of omega t. This equals 0 when omega t equals pi over 2. That's when a cosine function equals 0. It also equals 0 at minus pi over 2, but or was that 3 pi over 2? But the first time is at pi over 2. So t is equal to pi over 2 divided by 258. Just setting this equal to pi over 2 and solving for t. That's 6 times 10 to the minus 3 seconds. And then finally, C, just draw a graph of the current versus time, I versus t. Let's see, it's cosine function, so it starts out here, right? Cosine of 0 is 1. Start out a little higher. And it quickly decays. It's a cosine function with an exponential function like that. All right, number 16, this last one. In this figure, the magnetic field changes as this function, 6t plus 5t squared. The area of the loop is this, that's my area. The wire has a resistance, that's R, here's my B. What is the magnetic flux at t equal 2 seconds? Well, gosh, this is just 6 times 2 plus 5 times 2 squared, and that is equal to 32 Tesla. Now, what is the magnitude of the EMF induced at t equal 2 seconds? So B, this one's more involved. A couple things you have to do. Actually, let's see. Oh, I'm sorry. No. I need to know the magnetic flux at t equal 2 seconds. So my flux is equal to the integral of B dot dA. In this case, B and A are perpendicular to one another, so this is just the integral of B dA. Dot product goes away because they're in the same direction, those two vectors. And then also B is not dependent upon A, so this just becomes B times A. So that's 32 Tesla times 0.01 meters squared. So that's 0.32 Tesla meter squared. That's my magnetic flux. Now I want to know what is the magnitude of the EMF. Well, the EMF is equal to negative N d phi dt. The N, I only have one turn, so I'll just leave it off here. And the negative, that has to do with our direction, so we'll forget about that for now. We're going to worry about use Lenz's law. But this is going to be equal to, our d phi is going to be A times dB over dt. Right? I basically use this definition here to say that my d phi is AdB. My area is not changing, it's just my magnetic field, so that's why the area is not inside that derivative. So this is equal to the area, which is 0.01 square meters, times the derivative of B with respect to t. That's going to be 6 plus 5t, excuse me, plus 10t. And at t equal 2 seconds, this is going to be 0.26 volts. That's the magnitude. And then I need to know the magnitude and direction of the current in the loop. So I need to know now what is the direction of the induced EMF in this loop. So I have this flux that is increasing. That means that the magnetic field produced by this loop is going to be, I'm sorry, I just couldn't resist, is going to be out of the page like that. The magnetic flux is increasing. That means this magnetic flux is increasing. So the induced magnetic flux will be opposite the direction of this increasing magnetic flux. A magnetic flux in this direction is going to be caused by a current going counterclockwise. You can do your right-hand rule like we did for the solenoid. That means that I have 2 volts in this direction, but I have 0.26 volts in this direction. So that means my net EMF is going to be equal to 2 minus 0.26 equals to 1.74. Okay? That means my current, which is E over R, is going to be 1.74 volts divided by 3 ohms, or 0.58 amps, and it's going to be in the clockwise direction because up here my 2 volts is bigger than my 0.26 volts, and so my current, my net current, is going to travel in this direction, but at a value less than what we would see with the 2-volt battery. And that is the end. There's our multiple choice answers.